Swayam Prabha. Digital India. Educated India.
So, students, we meet again for the third lecture on shear strength of soils. We have had two lectures where we had covered quite a bit of ground on certain very important concepts relating to shear strength of soils. Notably, we spent a lot of time in understanding an elegant graphical procedure called the Morse circle procedure for determining the stresses at a point on any arbitrary plane. You may recall that the reason why we did that was we need to know what is the stress acting on any given plane and to test according to some strength criterion or failure criterion whether or not shear failure will take place along that plane. And that is what shear strength of soils is all about. Given a set of stresses, will the soil fail, and if so, along which plane, and that is what we will be able to determine once we know the so called shear strength parameters or the strength parameters of a soil against shear. Today, we will go further ahead from what we saw in the last lecture. We shall go ahead and see some typical strength tests which are being usually done in order to get the strength parameters, the so called cohesion and friction of the soil. There are many methods. We had in fact briefly gone through all these methods as an overview in the first lecture. In today's lecture, we shall be covering some of these tests in some detail. We may have to devote one more lecture to understand these tests a little more in detail. The first test that we shall be seeing at some length is the direct shear test, DST. The second one is the triaxial shear test, TST. The third one is the unconfined compression test, which is sometimes called as unconfined compressive strength test, UCS, or sometimes it is called as the UCC, unconfined compression test. The last one is the vane shear test. We shall be seeing essentially the first two, which I have marked here with this symbol. We shall see these first two tests in detail today. We may have to devote some more time to study them a little more in detail later, and then the last two we shall take up later. And whatever we see today, I will illustrate with a couple of examples as well. Now, there are many ways in which this topic of shear strength can be presented. After all, what we need is what is the shear strength of a soil. Now, the shear strength of a soil depends on many factors. So, depending upon the factor that you are using as an yardstick, you can study this chapter of shear strength of soils in different perspectives. If you are looking at the type of test that is being conducted, the equipment that is being used, then we have the classification which I showed you in the previous slide, that is the direct shear test, the triaxial shear test, the vane shear test, and so on. The yardstick that has been used is the way in which the shear test is being conducted. In the direct shear test, as we will be seeing, there is a predefined plane along which the soil is sheared. In the triaxial shear test, on the other hand, we try to simulate the natural actual site stress state and then allow the soil to fail along the weakest plane. In the unconfined compressive strength test, which is a very special case of the triaxial shear test, once again we allow the soil to fail along the weakest plane. In the vane shear test, we create a failure plane by rotating a vane inside the soil and try to study what is the resistance that has been mobilized along that known plane or surface. Another yardstick that we shall be seeing, perhaps not today, is the type of test conditions that we provide during testing. Notably, the condition with respect to movement of water. You know how important water is. Whenever we shear a soil which is, say, saturated or which has water in it, the water will try to move out. Now, if you do not provide the facility for the water to move out, or if the soil is not pervious enough to allow the water to move out at a reasonable rate, then we have what is known as the undrained condition. Under all other circumstances, when water is able to move out freely, flow freely out of the sample which is being tested, we have the drained condition. So, depending upon the type of condition that you use, whether it is drained or undrained, the soil will mobilize and exhibit or manifest different strengths. And therefore, the type of test is important, and we can use that as an yardstick for dividing the different types of tests and understanding them. There is also another yardstick, that is the nature of the soil itself. Is the soil cohesive or cohesionless? Depending upon the type of soil, its response will vary according to the type of test we conduct, and therefore, we need to also study the type of soil and its effect on the shear strength. So, these are the three possible yardsticks. Let us see what is the importance of type of equipment that is used and what is the type of test that we conduct. So, we shall be now seeing the direct shear test. First test that we shall see in detail is the direct shear test. Now, here is a diagram showing a schematic of the direct shear apparatus. See here, this is a metallic container. This, what you see here, is a metallic container. This upper portion is a part of the same container. The container is split into two halves, and there is what is known as an yoke to which a proving ring can be attached, is fixed, and the soil specimen is kept in this container, and the specimen again is kept in such a way that there is a small gap between the two parts of this container, so that the upper portion can be moved relative to the lower portion. Then on this side you have dial gauges to measure the movement of the upper part, and then on top of the specimen we have here a loading plate on which is the normal load applied. So, effectively what we have tried to do here is, we have taken a sample of soil, we are trying to apply the kind of load that it is experiencing in the field, and then we are applying a shear force, a tangential force, and make it fail, and then see how it fails and what is the resistance that it has mobilized at the time of failure. So, the components of this so called shear box are, there is this container, then there is this cap which is the loading plate, there is a dial gauge to measure displacement, there are rollers to permit the bottom portion also to move if required, there is a porous stone at the bottom of the specimen and at the top, and there is a dial gauge at the top again to measure the volume change that will occur when the specimen is sheared and the upper portion tends to move outward and upward. These porous stones permit drainage of water. Now, as I said, drainage is very important. depending upon the condition of drainage, whether we allow drainage or not, or whether the drainage allowed is slow or fast, depending on these conditions, we will have the so called drained or undrained state, and the behavior of the soil will vary. And we shall be seeing shortly how these drained conditions really exist in a direct shear test, do they or not. Here is where we apply the shearing force. This green arrow shows the shearing force. So, in effect, this describes what a shear test, direct shear test is all about. The specimen is typically 6 centimeters by 6 centimeters in plan area and 10 millimeters millimeter in each half. So, a total of 20 millimeters. A normal load is applied first, that simulates the confinement that the soil is experiencing in the field. After you apply the normal load and after you are sure that the confinement and its effect have been recreated, then we apply the tangential force until failure occurs. And the tangential force at failure divided by the area of cross section is the shear stress that the soil is subjected to. And now, at the time of failure, if you plot the shear stress and the normal stress for at least 3 different tests with soil specimen molded at different moisture contents or different densities, and we plot a graph which we shall be seeing later, we can evaluate and get the 2 shear strength parameters, cohesion and angle of internal friction. Let us proceed. Here are 2 views of direct shear test. Here is one direct shear test, very old and very conventional. Here is a slightly improved and better version. The difference is in the application of the normal load and shear force here. The second one, the diagram on the right hand side, it is a motorized device to apply the shear force. The components of these boxes are: 1, specimen. So, this is where the specimen is kept, this is how the container looks. The normal load is applied here through this lever arrangement. Here also you can see this lever arrangement for applying the normal load. Then comes the motorized shear load application. Here you see the motor here, and here the motor is not very visible, but there is a motorized arrangement here as well. In earlier versions of this, the application of the shear load was also manual. And then we have the proving ring to measure the tangential load, and then the dial gauge here to measure the vertical displacement. So, this is how a direct shear apparatus looks. There are 2 types of test devices. We have to apply a shear force to the soil. We have to allow drainage to take place if we want to do a drain test. All this implies that there has got to be a certain rate of shear which should be sufficiently slow, considering the type of soil we have, to permit water flow. Obviously, the rate of shear will vary depending upon the type of soil, its porosity or its coefficient of permeability and the flow of water. Therefore, we need to have the facility to have different shear strain rates. It is possible to also control the application of the shear force not only by controlling the shear strain rate, but also by applying the load itself in increments in such a way that the shear stress applied is in certain increments. So, we can either control the strain at which the movement takes place, or we can control the stress that is applied. Accordingly, we will have a strain controlled device where shear deformation is applied at a constant strain rate till failure, and even beyond if we are looking for testing beyond the failure state as well. And it gives good loading control, because it is very easy to have a mechanical device or an electromechanical device, a motor to be precise, by which a constant strain or a constant rate of movement of the shear box can be very easily achieved. On the other hand, we also have this strain controlled equipment. We also have this stress controlled equipment, where the shear load is applied at uniform increments until deformation ceases. Here it is very difficult to identify the point of failure as we have done in the strain controlled equipment, and therefore, we keep loading in uniform or equal intervals until we find that for any given load the deformation comes to a halt, and then we apply the next increment, and this goes on until the sample finally fails. Now, let us take a look at the same two equipment once again. Both of these are conventional equipment, both are strain controlled, because here there is a motor, here there is a motor, which makes the upper portion of the container here to move at a uniform rate of displacement. Same thing here. On the other hand, here is an equipment which is very sophisticated and microprocessor controlled. It is also a strain control device, but it is digital. It gives you all digital displays. It gives you 100% control over application of loads, both normal and tangential. So, this is the latest modern version of the direct shear apparatus, also strain controlled. The stress controlled apparatus does not look very different. It is just that in place of the motorized arrangement for application of the shear force, we have a slightly different chain based arrangement by which a load is applied in increments. Let us take a look at how shear takes place. You can see here the upper portion of the specimen is moving relative to the bottom portion, and simultaneously, depending upon the movement, the shear stress by normal stress ratio goes on increasing, and what you see here is typical of a dense sand under direct shear conditions, and you also find that this upper part has moved up by a certain amount delta y. This is due to the volume change in the sand as the shear force is applied. Despite the existence of the normal load, there is a vertical movement upward due to volume change or dilatancy of the sand. And if you plot the displacement itself as a function of the, if you plot the vertical displacement as a function of the shear displacement, you will have a graph like this. This is again for dense sand. What you see here is in the first upper plot, that in case of dense sands, when you induce a shear displacement, that is when you conduct the direct shear test, as the shear displacement here, this delta S goes on increasing, the shear stress to normal stress ratio goes on increasing and it reaches a peak, and after further displacement it tends to come down and it reaches an ultimate stage. This is very typical of dense sands. One of the reasons is, as you apply shear displacement, a dense sand tends to become loose, and as it becomes looser and looser, at some point it starts showing lesser showing a downward trend in the shear stress to direct shear, shear stress to normal stress ratio. For example, the shear displacement shows how the expansion takes place. Initially, even in a direct shear test, there will be a small amount of compression due to seating arrangement. When you apply the normal load, there will be a small amount of compression taking place, and when you apply the shear load again, a little bit of compression initially takes place due to adjustments against the applied load. And then if the sand is dense, then gradually it tends to become loose and loose as the shear takes place, and this is how the trend is, and you find from compression we have now moved to expansion. And this point, this stage at which this expansion goes on taking place is a stage at which the shear stress at failure comes down. Now, this can be taken as a point of failure corresponding to the peak shear strength, but if you continue the test further, you have a point at which a steady state is reached, and this may be considered as the ultimate strength. Both have their significance in practical application. Let me mention it here at this stage for completeness sake, but we will see it again later. The peak shear strength obviously is the maximum shear strength that the soil can have, but that is related to this shear displacement, this amount of shear displacement. Now, in an actual problem in the field, if the shear displacement is confined or it is within this limit, then it will reach the peak stress state and it will enjoy the peak strength. But if the shear displacement, expected shear displacement in an actual practical situation is much more than this displacement, then we must understand that the sand, dense sand in this case, is undergoing a large amount of displacement, and at that displacement it is not likely to have its peak strength, it will enjoy only a much lower strength. And any design that is based on this test should make note of this, and if it is a problem in which there is going to be a long duration and a large shear strength, shear displacement taking place, then we should be careful enough to consider the ultimate strength rather than the peak strength. Further, suppose we have loose sand, the phenomenon is just the opposite. In the case of loose sand, as we apply shear displacement, the shear stress to normal stress ratio of course goes on increasing, but it tapers off here, it does not reach a well defined peak, nor is there a drop at large displacements. This is again because the phenomenon is exactly opposite of what takes place in the case of dense sand. In the case of loose sand, there is a contraction taking place as the particles readjust themselves under the action of the normal and the tangential loads. When the particle readjust themselves, they can move up or down, and then the net movement is downwards, it is a compression as the soil gets denser and denser. So, here the shear displacement versus vertical displacement graph for loose sand is this bottom one here, which is a continuous compression. This is a very simple illustration of what happens during direct shear in a typical coarse grained material. There can be variations, of course, minor variations can be there, and this is only typical of coarse grained soils like sand, but when you go to clays or silts, the behavior is not the same. Now, let us see what is the state of stress that prevails in a direct shear test, because that is what is most important. We need to know what is the state of stress, so that we can define what is the state of stress at time of failure and what is the mode of failure that takes place. But after all, here we are making the soil fail along a predefined plane, and therefore, the failure plane is already decided, and correspondingly all other planes will have their appropriate stress values, which if we need to compute using either the Morse circle or by a theoretical analytical formula. So, let us take the example of some determination of important stresses using the Morse circle in a direct shear test. We have the normal stress, we have the shear stress, the two axes typical of a Morse circle. Then we have, suppose we have the sigma and tau values at failure, then sigma tau values at failure will belong to a point C typically as shown here. So, this point C has coordinates sigma and tau, and that should correspond to the normal stress and shear stress on this failure plane, because that is the point at which the Mohr envelope touches the circle, and therefore, this point C corresponds to failure, and therefore, the Mohr envelope should pass through that, and that should be tangential to the Mohs circle. So, now we can draw a Mohs circle which will be tangential to this envelope at this point. Now, this being a drained test, direct shear tests are usually drained tests, cohesion is not mobilized, and therefore, this intercept on the y axis C due to cohesion is 0. Now, if this is the envelope and if this is the Mohs circle, obviously, the major principal stress will be OB and minor principal stress will be OA. It is of interest to know what are their orientations. Magnitudes are available now from the Mohs circle plot. Now, what are their orientations? For example, if you take sigma 1, to get its orientation, we will use the so called pole method, which we saw in detail in the last lecture. Take this point C, that is a point whose stresses correspond to that, or rather those on the failure plane. Therefore, this point C is a point on a plane which should be parallel to this failure plane and must intersect the Mohr circle at the pole. So, point C, if you take and draw a line parallel to the known failure plane at C, then it intersects the Mohr circle at the point OP, which now becomes the pole. The property of the pole is that from the pole, if you draw a line parallel to any plane, where it intersects the Mohr circle gives you the stresses on those planes. So, for example, if I draw a line up from OP to point B, since the coordinates of B have major principal stress and 0 as the values, OPB must therefore represent the major principal plane, that is this yellow line, because it passes through a point B whose stresses correspond to the stresses on the major principal plane, that is sigma 1 0. So, the major principal plane is very easily obtained once you know OP by connecting it to point B. Identically, by the same method you can get OPA, which will be nothing but the minor principal plane. So, now we know the orientations of the major and the minor principal planes. If I transfer them to this direct shear index diagram which I have here, index sketch which I have here, then this yellow line represents the direction of the minor principal plane, this pink line represents the orientation of the major principal plane, and this means that although before failure the major principal plane is horizontal and the minor principal plane is vertical, at the time of failure the horizontal plane becomes failure plane, and therefore, automatically the major and the minor principal planes take up new orientations as given by these two lines. And this angle which the envelope makes with the horizontal will be the angle of internal friction. And if I join A to C, AC, that will make an angle of 45 degrees plus 5 by 2, as it should. Okay. Now, this is how we determine the stress state in a direct shear test at failure. Now, let us see a couple of examples to illustrate the direct shear test. This is a simple example. It reads like this: direct shear tests were done on a dry sandy soil. Now, I think at this point I should also elaborate. I am giving the example of dry sandy soil. The reason is I want to simplify the problem and illustrate for a very elementary case. Direct shear tests are usually conducted as drained tests. The reason is it is very difficult to prevent drainage in them, as you will see a little later, and we therefore usually conduct direct shear tests on sandy soils or cohesionless soils. The reason is these soils are rapidly draining, and therefore the drainage condition becomes irrelevant. as long as drainage is permitted. Now, the shear strength of the specimen under such drained state in a direct shear test can be very easily determined if we know the normal stress, shear stress values for at least 3 tests. So, here is an example where the normal load, normal stress, shear load or tangential force and the shear stress are known for 4 different tests. That means, tests have been conducted under 4 different normal stresses and corresponding 4 different shear stresses at failure have been noted. Now, from these set of sigma n and tau values, it should be possible to determine C and phi. We can adopt the Morse circle principle. Let me go back a little bit. We see here that the Mohr envelope is tangential to the point C, for which the coordinates are sigma and tau, which means that if I take the 2 axes and test by test, if I plot sigma and tau corresponding to failure, I will go on getting points C1, C2, C3, C4, 1 each for each one of the tests conducted. So, rather than drawing a complete Morse circle, if I could just draw the xy axis shown here and plot these points C1, C2, C3, C4 of the 4 tests and join those C points, the angle that that line will make with the horizontal will be the angle of internal friction. By doing 3 or 4 tests, we get an average value using the best fit line through all the C points. Next one. So, we now here have normal stresses 50, 100, 200, 300 kilonewton per meter square. These are certain typical normally used values, and the corresponding values of shear stress are 40.5, 82.0, 167.4, 247.8. You will notice here that these values are always less than this. It is very rare that these values will go above the normal stress itself, because as you will see, that will indicate that the angle of friction is more than 45 degrees. There are very rare instances where angle goes beyond 45 degrees. Of course, in the case of rocks, it does go beyond 45 degrees easily, but it is virtually rare in the case of soils, unless it is a very stiff soil. So, the sigma tau plot, as it is called, for this example would be like this. You take these normal stresses 50, 100, 200 and 300. They are all plotted to some convenient scale. To the same scale, remember, to the same scale, the shear stress values are also plotted 0, 50, 100 and 50 and so on, and these 4 points corresponding to the 4 different tests are plotted like this. You will notice that when they are plotted and joined, the line joining them will automatically pass through the origin, because this is a drained test where cohesion does not get mobilized, and here is the result for the first test. The intercept is 0, therefore, C is 0. Since the test is a drained test, the parameters that we obtain are known as the effective stress parameters. So, this C really means C dash, the effective stress parameter, and this phi really means phi dash, the effective stress parameter, and C is 0, whereas phi will work out to be the slope of this line, which turns out to be 40 degrees in this particular example. So, now we are in a position to get the values of shear strength from a direct shear test if we know the typical normal stress, shear stress values of at least 3 tests, preferably more, for any particular soil. Let us take another example. This example is also a very simple direct shear test, again on a dry sandy soil. The sample size is again 60, 60, 20 standard. We need to determine here also the shear strength parameters C and phi, but in addition I have added here another parameter, that is, what are the principal stresses. From these test results, can you calculate the principal stresses as well? That means, in the Morse circle which we saw earlier, we want to determine sigma 1 and sigma 3 values corresponding to the two extremities of the diameter of the Morse circle. Here the values of sigma and tau are 35, 50, 120, 170 kilonewtons per meter square, again somewhat typical values which are normally used, and corresponding shear strength is stress rather are 20, 31, 72, 103. At one glance you will find that these values are rather small compared to the previous test. This immediately gives us an indication that the value of angle of internal friction here is obviously lesser than what we got, must be lesser than what we got in the previous example, that is example number 4. Let us see how this plots. So, now if you plot these are the 4 points corresponding to the 4 different normal stresses and the shear stresses, and once again if you join these 4 points, the line joining these 4 points will pass through the origin because C is 0. Of course, in a practical situation sometimes it may not actually pass through the origin, but then it is fair enough to forcibly pass this line through the origin because C has to be 0 under the conditions of drain testing. So, here we have, after plotting like this, we get C equal to 0 again as it should be and phi is equal to 33. This means that this soil has got a slightly lower angle of internal friction compared to that soil and is therefore having less strength. Note here one important point which I stressed earlier, that is the scales for sigma and tau have to be the same. If they are not, we cannot directly read out the angle here and take it as angle phi. Angle phi will have to be then calculated as tan inverse of tau upon sigma, because the coordinates of this are sigma tau and the angle of inclination will be tau upon sigma, and unless the scales are equal, we are not justified in directly reading this angle and taking it as the angle of internal friction. This is the plot for example phi. It can also be seen that it is possible to plot a complete Morse circle for this, and if we do that, what we will have is, we already know sigma and tau. So, take a typical value of sigma and typical value of tau and plot them, you get the point C. Then you can draw a tangent to this. In the most general case there will be an intercept, but in this particular problem there will be no intercept and the Morse envelope will pass through the origin. And this point C being the point representing the state of stress in the on the failure plane, here a line drawn horizontally will represent the failure plane, and this angle as always will be the so called critical angle, and it can be obtained as 45 degrees plus phi by 2. OC is the strength envelope here, OC is the strength envelope here provided C is 0, and AC is the plane of failure. That is the under normal conditions, but in the direct shear test the plane of failure is forced to be horizontal. Now, let us see a number of important points which can be attributed to the direct shear test. Here I have on the first slide 4 points. Number 1 is, a direct shear test is good for relatively slow drain tests since it is open to permit drainage. What are we doing in a direct shear test? We are moving one part of the container relative to the lower other part, and in that process the specimen is continuously moving, and when the specimen is continuously moving, it is going beyond the cylinder or the container. See here, suppose this is the lower container and this is the upper container. Now, if the upper container is moved and if it takes a position like this, in this position this part of the specimen is exposed